Hello guys, this is Paul McWhorter from TopTechBoy.com, and we are here today with our live Shop Talk number 8, where we're going to be talking nanotechnology, MEMS, and micromachining. So I will need you to pour yourself a big mug of iced coffee, and I will need you to get ready to jump into the conversation, and let's talk about these topics. Maybe you guys could let me know how many of you are familiar with nanotechnology. For how many of you is this something completely new? But I think we have some very exciting stuff lined up for you today. Looks like we've got some people coming in. Hey, we got from South Africa, from the UK. All right, great. You guys are tuning in. And we will be talking about nanotechnology, and I think that that is very appropriate because I'm happy to let you know tomorrow we launch our new class on the Nonaxis IMU. You guys know that we've been talking about this, where I am going to step you through how to use a BNO 055 non-axis inertial measurement sensor to get full 3D visualization. Now, if you look at what most guys do with these cool little demos, notice they always just tilt a little bit. Okay. Not many people can flip the thing all the way over and can go into those 90-degree positions and then spin around those 90-degree positions. And so we're going to launch that class tomorrow. And what I'm going to do is I'm going to try to I'll try to make it a premiere. If I'm available, I'll make it a premiere so I can kind of be in the chat room with you guys as we go through that. It seems like we got a pretty good community of people ordered their sensors and ready to go on that project. But it's kind of an appropriate topic today because if you see this cool little device, it's like it knows where it is. How does it do that? How does it know how to do that? Nanotechnology, okay, nanotechnology, and that's what I'm going to kind of talk to you today about. I'll go through a little bit of a presentation, and then I will answer your questions towards the end. You guys feel free to chat among yourselves, you know, sit and get a little sense of community going, chat among yourselves, and then when I kind of get through this, I'll come back and answer your questions. Also, want to thank you guys that have been signing up to help me on Patreon. There's a link down in the description if you guys want to go over there, hook a brother up, and throw a little support this way on Patreon. One thing I can always promise you, all my content is going to be free, and it's going to be free for everyone. Kind of the thing people do, they throw out some interesting stuff to kind of get you hooked, and oh, but if you really want to see how to do it, go over to Patreon. I know that I know of, there's probably a dozen people that I know of over in Africa. I mean, these are almost like people living in villages in very, very remote places that are trying to learn electronics. Everyone has a cell phone. Almost everyone in the world has a cell phone these days. And so you go into these really remote areas and there's people that are trying to learn this stuff. So it's always going to be free. But you guys that are helping me out, appreciate it. Be great if a few more of you would do that. But enough of that nonsense, and we will move right into this presentation. All right, so how does this thing know where it is? Nanotechnology. And nanotechnology is something that I know a little bit about because I spent a lot of my career working on nanotechnology, and in fact I have some of the original patents and some of the really fundamental patents on nanotechnology, so it's something that I spent a lot of my life working on. And I think it's kind of neat now that I can go to Adafruit, and for a couple of bucks I can buy devices that are incorporating that technology into it. So that's what we're going to talk about today. So let's get started and answer the question, what is nanotechnology? Basically, I would describe nanotechnology as a way that you make very, very, very small machines, as shown here. Can't use a green pen. As shown here. That is a SEM micrograph of a gear that we made very far back in the day. And that is put beside some human red blood cells, so you can see that we are building recognizable mechanical objects that are the size of a human red blood cell, features the size of a human red blood cell. Now I'm going to show you some real cool stuff today. But the stuff I'm going to show you, it looks so cool, you're going to think that it's a computer simulation, but it's actually machines that we built, that we put under an extremely powerful microscope, and then we made the machines do things under the microscope. But when you look at these little things, it's like they're real, but they look like a computer simulation. So I'd briefed in my career everyone from presidents of the United States to congressmen. I mean, at least once or twice a week we would have a delegation from the Senate or the Congress come through. The sort of elite leaders of the world would come through and look at this. I'd say, okay, I'm going to show you what we built. And then I would project it up there live, showing them what we built, and then they'd say, wow, that is great. When are you going to really build these things? And it's like you couldn't convince them that it was real, that what they were seeing was live and real. And so we would even hook them up to joysticks, and then they could control them with the joysticks. And so we're going to see some pretty neat things. This is just a still image here of one of the gears on one of the machines that we built. I guess the first question that you probably have is, how do you build these things? How do you build machines that operate and that are the size of a red blood cell? And I'll kind of draw it out for you more later, but the quick answer is you build them the same way you build integrated circuits, right? Integrated circuits are built on silicon wafers. This is a 6-inch silicon wafer that's full of integrated circuits. Probably now, I don't know, like 12-inch wafer is probably the standard now, that as time goes on, the wafers get bigger and bigger, but I just happen to have a 6-inch wafer. So what do you know about integrated circuits? Well, you know that on something the size of a postage stamp, you can put like a billion transistor with a B, 1 billion transistors on a wafer. So you're building microscopic electrical objects, transistors. Well, kind of the idea back in the 90s is, hey, if I can use this equipment to build a microscopic electrical device, maybe I could try to build a microscopic mechanical device with that same set of equipment. And with that, kind of the field of nanotechnology was born. Now the cool word is nanotechnology, but back in the day what we called it was micromachining, because we were building machines with micron dimensions, 1/millionth of an inch, 1/millionth of a meter feature sizes, and so we called it micromachining. But then we started building circuits alongside the machine, so we started calling it micro electromechanical systems, because you had the electronics right by the machines. And so when we first started building these machines, it got a lot of interest. I mean, it really got a lot of interest. So let me see if I can show you kind of like one of the first things that we built with this is, okay, like if we're going to build a machine, let's build something pretty neat. So what we decided to do was to build the world's smallest steam engine, and the technology was a lot better than the technology was a lot better than our video camera back in the day. I think of kind of like what a great thing, what an amazing thing this was that we did, but then we kind of had a lousy video camera. So let me switch over and show you the world's smallest steam engine in operation here. How do I switch over here? Let me find the right view. This darn thing wants to stay small. Let me see if I can. It's kind of hard having to be the on-screen personality and the control room operator at the same time. I said, big, you aggravating thing. Why won't you stay big? It doesn't want to stay big. Okay, but let's see if we can. Let's see if we can work through this. All right. So what you see here is in operation an actual video. Oh, this is going to make me mad. I'm going to try one more time here. Let's say full screen. Maybe it will decide to cooperate. All right. Maybe I need to get a little bit further out of your way. All right. Maybe this is going to cooperate. Okay. And can you see my mouse? Hopefully hopefully you can see my mouse a little bit. Look closely for it. So do you see this is the piston, and it's coming out and it's going back in? And so the way this works is this is sitting on a silicon wafer, and we made it just like a transistor. So we didn't make one world's smallest steam engine, we made a bazillion world's smallest steam engines at the same time, because it's no harder to populate the whole wafer with them than it is just to build one. So I don't know how many millions or billions or whatever were on there, but you made a whole lot of them. And the way this works is this is a silicon wafer, and then this is polycrystalline silicon. That is silicon that's deposited on top of the wafer. And in this area is the boiler. Okay, this area is the cylinder, and then this is the piston. And the piston is like 2 microns across. Again, a human hair is about 100 microns across. A sheet of paper is like 100 microns thick. Human blood cell is like 10 microns across, and the piston on this engine is 2 microns. And then inside of the boiler is a resistive heater, so it's a little resistor in there. And then we put this in water, and the water, through capillary forces, goes in small gaps and fills the boiler. And then when we put a voltage between this pad and this pad, the heater turns on, and when that heater turns on, it makes a little bubble of steam and it pushes that piston down. And then when we turn the heater off, the bubble condenses and the piston is brought back in. So since we are expanding and contracting a little steam bubble, this doesn't work very quickly. But when people realized what we had done, it just blew them away. And so all of a sudden, everybody wanted to come, and everybody wanted to talk to us about these microscopic machines that we were making. And I'll show you just a couple of seconds of one of the things. This, we had CNN come in a number of times, Fox News, ABC News. Everybody came in wanting to do stories on this. But this, I'll just show you a little story here. Let's see if this will work. I hope this.
This is amazing. Soon machines so small
I hope you can hear it.
May be part of everything, even your body. Watch ABC's World News Tonight with Peter Jones.
Are you guys able to hear that? I hope so.
On World News Tonight this Friday, the fantastic machines which are the speck of dust.
In 5 to 10 years, they'll be part of virtually every product that you buy.
Hey, do you recognize that's the younger, fatter version of me? That was probably 20 years ago, so I don't think I've changed that much. It's just like the hair's gone white, a little bit more facial hair, but man, I was eating out too much back then. I'm glad that I've lost weight since then.
Technology on the cutting edge. When we were putting together our report for the Cutting Edge tonight, we were reminded of the old science fiction movie The Fantastic Voyage. It was, you may recall, about some scientists who were shrunk to microscopic size so they could travel inside a person's body. You'll understand what brought it to mind when you see what ABC's Brian Rooney has found. So think small.
The technology that might change the world is simple machinery with cogwheels and drive shafts. It's technology that's been around thousands of years, but this is a little different.
This is how big?
The gear tooth that you're looking at is the size of a red blood cell. The gear is roughly the size of a grain of pollen.
These are micromachines, so small they can't be seen by the human eye. A dust mite looks like a monster compared to the microscopic levers and gears. These machines are so light they're barely affected by gravity. Micromachines are small, but they're going to be big.
In 5 to 10 years, they'll be part of virtually every product that you buy.
They're already part of the mechanism that sets off a car's airbag, and new uses for micromachines.
Okay, so you kind of get the idea. There was a lot of excitement about it, and so I was on TV a lot. Probably once or twice a month, there would be some, national. Drop the microphone. Is it still working? Hello? That probably was somewhat alarming to you. The good news is at least I haven't spilled my coffee this time, right? At least I have not spilled my coffee this time. So we're doing good. I hate it when I spill my coffee, but I did drop the microphone. All right. So there was a lot of interest in it, and a lot of very high visibility, for the work. But before I kind of talk to you, what I want to do is I want to show you some of the amazing things that we were able to do. Then what I want to do is I want to go in and give you a little bit more depth of understanding of how we built them. Okay, how we build them, and then I want to kind of talk to you about how they're used. Like, how is it that those little machines or things like those little machines are used to make something like this B&O 055 inertial measurement sensor work? And so let's see, what would be the best way to do this? I really hope that we can make this thing stay full screen. It's really bothering me how it keeps going smaller. So I showed you the steam engine, and that was just kind of like one of our very first early attempts just to make something move, something that something that we could call a motor. And it really was a motor. It really was a steam engine, okay, but it was just that first time that we got motion. And then we started doing things more sophisticated. So you might ask, why would you want to move something at these microscopic dimensions? And what we show here is this is a microscopic mirror on the surface of a wafer, and so what you can see is it's popping up and then it's dancing around like this. So why would you want to make a mirror dance on the surface of a silicon wafer? Well, think about the internet, think about cell phones, think about telecommunications. What is that? Now, it might come from the box in your house, around your house, as electrical signals, but that's kind of like the town traffic, right? The interstate traffic, it is all optics. And so there's kind of like fiber optic cables all over the world, and the data goes down those fiber optic cables at the speed of light because it's optical. But then when you come to the end of the fiber optics, you got to switch those signals around, and that's where the log jam happens. That's where you leave the interstate and get stuck in the traffic jam. And so the interest in this type of thing is to build optical switches that allow you to switch signals for telecommunications and things like the internet without having to stop, unpack, sort everything, repack, and then get back in the car and go. So the choke points of the global telecommunications infrastructure is where you have to take those optical signals, change them to electrical signals, switch them, and then launch them again as optical signals. So what the real interest was in doing all optical switching. And you see you could do that. And this is really, if you look at this, this is very controlled operation. You can see that we are really tilting that mirror a very significant amount. Some more just pictures of mirrors. So a lot of the stuff we did in the first practical applications, well, I think that video said one of the first uses of this technology was for airbags. And if you think what an airbag needs to know is it needs to know if there's been a car crash. Well, what is a way to discern that there's been a car crash? It's rapid deceleration. So while this is a non-axis inertial measurement sensor, back in the old days, it was like one accelerometer, and you look for rapid deceleration, and if you saw rapid deceleration, you knew that there had been a crash, and then you fire the airbag. Okay, so that was like one of the first applications, and the technology, the mechanism for that is relatively simple compared to what I am showing you here on this mirror. But let me show you just kind of another view of a mirror here. And this again is microscopic in dimension, but you can see that the mirror is out on these arms, and then you're pulling the mirror up and down, and we're getting just huge amount of motion. So this isn't like the steam engine where you barely got it. This thing is moving over very wide ranges and precisely controlled. I mean, we could control this to a crazy level of precision because of the precision with which it was made. Let's look at another Another mirror. Okay, that first one you saw was just kind of going up and down, but this one we kind of have swimming. Okay, I hope you guys can see that. And again, this thing dimensions the size of a red blood cell. And also what you don't see out here, you see the mirror moving. Okay, you see the mirror moving, but what you don't see out here is this is where all the magic is happening, and there are tens of millions of mechanical elements that are creating the motive force, the motion force that is then leading to this mirror. So you can see we can make the mirror go up and down, we can make it tilt this way, or we can make it tilt this way. So pretty sophisticated amounts of motion. Let's see what else we have here in this crazy in this crazy vault that I'm opening up. This is stuff like from my vault that very few people have actually gotten to look inside the vault and see some of the stuff that we made. Because when we were making this, you didn't want people to know what you were really doing, so you typically didn't show it to anyone. Okay, but I digress. Let's see. Let me look at this. Okay. Oh man, this one, it cut off too soon, but this was this is the motor. So you're seeing a close-up of the motor that makes the mirror move. This was that earlier swimming mirror, the round one. And what we did was we put a ruby on top of it. That sphere is like a microscopic ruby. It would be kind of like one of the jewels in like a fine Swiss watch. And this video cut out too quick, but what we did is we raised the mirror real quick and we made like a catapult, and we threw the thing off. But this was the setup video, and this one got cut off before it actually launched, but I apologize. But this one we will. You want to see launch? Okay, let's look at launch. This is the world's smallest crossbow. And again, guys, I swear this is real. This is not a simulation. This is right off the microscope. And let me kind of, oh my goodness. Can I pause this thing? Okay, yeah, there it's paused. So what you have is, this is an electric motor here that goes up and down. And this is an electric motor that goes sideways. You can't see that other one, can you? So I need to go to a more suitable view. Let's see. That one's kind of annoying, isn't it? I think I'll just fix this one if you guys will give me just a second. Again, it's hard to be the the speaker and at the same time be doing the control room stuff. Okay, so over here is you can't see that. Over here is a motor that goes left and right. Up here is a motor that goes up and down, and then we run those motors just right, and then that spins this little gear. Well, what we're trying to do is make a crossbow, and that's really hard to pull that crossbow back because these are very, very stiff elements. So we have a small gear driving a big gear with a small gear on top of it driving a big gear with a small gear on top of it driving a big gear. So this is like a 1,000,000 to 1 torque increasing system with this transmission. Again, feature size is the size of a red blood cell. And then what it is doing is pulling this back, this straight bar here, it is pulling it back. And then you will see these things are like the bow and arrow. So it's like 1, 2, 3 bows and arrows. And so let's go ahead and run this thing. And let's see, is that running now? Yeah, there you can see it turned on. Do you see that thing cranking? So this little gear is spinning like, I don't know, 100,000, couple of 100,000 RPMs, and then that motion gets stepped down, stepped down, stepped down, and the torque gets stepped up. And if you look over here, you can sort of see it start looking like a bow. Okay. But what we're going to do is we are going to electrically blow a fuse here. So we're going to release that thing all at once. Look at that. Do you see that? It's like we're pulling that bow back, and there is a tiny little pellet here. And what we're going to do is, how are you going to, okay, look at that bow, man. Do you see how that thing is pulling back? This is our fuse that we're going to blow to release that energy. And then we have this little pellet, and we're going to launch that pellet like hypersonically, like we're going to hit that pellet at hypersonic velocity. And the pellet is like tiny. It's like way smaller than a red blood cell. Boom! Did you see that release? We blew the fuse. Now look down here and watch this little projectile. Do you see the little projectile? Watch. Wait for it. Wait for it. Boom! We hit that thing and launched it like with hypersonic velocity. Now, unfortunately, I can't tell you why we were doing this, but it was a very, very interesting and very important project. Let's see what else we have. Okay, this is a little cell chomper. What you can see is we're running fluid through. There's like a little tube, microscopic, really microscopic tube, and we're running fluid through it, and then we created this little motor that as those blood cells went through, we could kind of crack them. We don't want to smash them, but we wanted to just break their sort of outer shell. I'm not going to tell you why, but I'm just going to show you what we actually did. Okay, let's see. This was another mirror. A lot of the stuff we did was mirrors, just because that application was so important. Okay, here you see how we pop that thing up, and now watch, we let it down, and then we make it kind of dance. And this isn't just randomly going. We are controlling that thing with micron position. Now you see how it's tilting towards us, and now it's tilting this way. So you could kind of think of that as roll and pitch, and we're getting roll and pitch and down, and then pop up. Okay, this is the thing that we put that ruby on, and we could launch that ruby. It was kind of fun. So what have we got going here? Out here we have the electromotive force, and so out here is where the magic is happening, and that is creating the little motion. And then through a series of levers, oh yeah, we called that the Death Star, just because it looked like the Death Star, so we called it the Death Star. And these are 3 motors out here that are generating the motive force. And then through levers, we're levering up that motive force, and then we are creating unbelievably precise motion in this mirror. And so we could aim that mirror anywhere that we wanted to, and because we could aim the mirror anywhere that we wanted to, we could switch an optical beam with precision, because it's very hard to get light into a fiber, and a fiber is tiny, and not only does the beam have to hit the end of the fiber perfectly, it has to be coming square on. So like if you hit the end of the fiber like this, the light's not going to go in. If you're lined up and miss it, it's not going to go in, but it's got to be lined up, and it's got to come in orthogonally. And so you've got to be able to switch light very, very, very precisely. And this was just kind of a little bit of a lame video, but here you can see that mirror, you can see that flashing laser. The laser is pointing at the mirror, and then we're switching that laser all around. And of course, real telecommunication is not done with red lasers, it's done in the infrared. But then again, that would not have been a very impressive video, would it, if you couldn't see anything? This was a ratchet. Do you see? This is a microscopic ratchet. Do you see that center part? Let me pause this silly thing. Okay, do you see this center part? It's vibrating back and forth. It's going like this. Okay, but then here is a ratchet mechanism, and then the output is just going one way, and then that goes out and drives a transmission. So we're taking reciprocal motion and we're changing it into useful rotational motion. Boom. Okay, I thought that was pretty cool. Again, and these things are made for a fraction of a cent. Because when we made the machines, you weren't just making one, you were making a bazillion across the surface of the wafer. All right, I should have shown this first, because this was one of the first mirrors that we made. This was one of the first mirrors that we made. And here what you can see is we've got that motor with those linear actuators, and it's spinning the gear. and then that is going through a transmission to step up the torque, and then that is causing, it's like a rack and pinion system, and we're driving that rack and pinion back and forth. And then what you're watching is you're watching the mirror pop up like this. So I think this was like our first attempt at building a mirror and switching a laser. And the problem is all of those joints are kind of sloppy, so you weren't getting like atomic precision in how you were pointing. And so that then is why we went to something, I don't know, maybe I wasn't supposed to show you that one. Get off of there before I get in trouble. Get off of there. Okay. Anyway, let me find the one that I am really looking for. Give me a second. Give me a second. I thought it was this one. I keep showing that. Stop that. Stop that. Where was it? Oh well, we'll just have to go with this one here. Okay, but you see this one is made where there's no rubbing surfaces. Okay, and you think mechanical elements break. They don't break because they move, they break because you have rubbing surfaces. And so what we learned really quickly was you didn't want any parts to rub, so this was made with no rubbing surfaces. It was made simply by bending and flexing, and no parts touching, no parts rubbing. And so when we did the real mirrors, they operated like this. Okay, now I'm not going to show that other one. That I'm not going to click on that again. Okay, but I'll say here's kind of a cool application. Let me see here. Let me see. What was this one? Okay, this is just looking at that mirror, and it's popping up and down. This was the one that we saw going like this that I don't seem to be able to. Oh, it was the Death Star. Okay. This is that same mirror I just showed you from the side. But you see, we get this level of precision by going to an architecture where we're not using anything that touches or rubs, only bending and flexing. Okay, so imagine that you had something really important that you wanted to lock, and an idea, and let's say you can't use an electronic lock because because that you can bypass the lock with like a high voltage. So like you think of like these digital safes, some of those things you can come up with a high voltage and you can just I guess I shouldn't be talking about how let's just say that electronic locks are not secure. I shouldn't be giving you a how-to of how to defeat locks, but electronic locks aren't secure, and so for some really important things you want to use mechanical locks. But then what if somebody could pick a mechanical lock? Well, what if you made a mechanical lock that was so small that it could never be defeated because you could never find it, and you couldn't pick it if you couldn't find it, and you couldn't find it if it was microscopic in dimension? And so let me show you an example of this. Okay, so what this is let me stop this. Okay, do you see down here you have like this tortuous path that is etched in that long bar? Well, what that is that's a series of decisions, and there is a pin here that is in that maze, and at every bit you have to make a decision to whether to go up or whether to go down. And if you go up when you should have gone down, you're going to end up in one of these dead-end paths, and once you end up in a dead-end path, you can't back out. So you have one chance to enter the right combination, and if you enter the wrong combination, then you are stuck forever. So if there's one bit, you've got a 50-50 chance of getting the combination. If there's 2 bits, there's a 1 in 4 chance. 3 bits, a 1 in 8. And so you can see by the time you get to 32 bits, even though each one is just up or down, you've got a bazillion different combinations. Okay, and so you can see out here that we have the little motor, we go through the transmission, and then we come down and we are driving this platform left and right. as we are putting this pin up and down, okay? And so then what we have over here, I think I got to turn this little thing off so you can see better. All right, so what you see here is we have got a little platform, and that platform has 2 gears on it. Well, there's another mirror that we're going to elevate to unlock the system, but there's no way that you could accidentally elevate those mirrors because in the gear train there's 2 missing gears. And the only way to get those 2 missing gears in place, I look kind of goofy there, don't I? I hate it when I look goofy. It's like I'm floating. I'm sorry. We got to fix that. Okay. How about that? All right. So we got a platform over here, and I'm just joking. I'm not telling you anything I'm not supposed to tell you. It's just I didn't want to show that video because it was not the video that I was talking about. So there wasn't anything that I wasn't supposed to show you. Okay. It's same thing here. This is something that I can show you because it was we were exploring ideas, okay? So that mirror has a drivetrain with 2 gears missing. So even if you got in there and turned the motor on, you couldn't align the mirror because there's 2 gears missing. Those 2 gears are here on this platform. How is the only way we can get that platform all the way across? If we enter the combination right, and then it'll move all the way across, it will engage those missing gears, and then you could activate the system. So have some coffee, sit back, and enjoy. Okay? Since I know the combination, I am successful. Do you see this moving up and down over here? Do you see that? Up, and then down, and then down. So it was like up, down, down. And maybe we're going to zoom in. This is the motor this is the motor driving that pin. Okay, went down. Better go down. What's the next one? Down. What's the next one? Guys, can you see the combination? Up. What's the next one? Up. What's the next one? Down. Can you see that? We've almost got the combination put in. So then we come across here. We've got the 2 missing gears. And what you can see here is this gear is not connected to this gear. So if we want to complete the gear train, we're going to plug these things in here. The combination is correct, and then it's going to release the brake. So the brakes are pushed back, armed, and boom. Over here, we pop the mirror up, okay? So the reason I show you this is a pretty darn complicated machine. Feature size is the size of a red blood cell. Okay, feature size is the size of a red blood cell, and made millions, bazillions at a time at the cost of a fraction of a cent. Okay, so I think that that is pretty cool technology, if I say so myself. Okay, let's see if I've got any other. There's a lot of videos I have, but I think you get the idea of what we can do. So that is the same technology that goes into this non-axis sensor, which, as we said, we will be launching this tomorrow. We will be launching this series of classes tomorrow, right?
I didn't find any appointments about series of classes for tomorrow.
Go away, Siri. Go away. We've talked about this before. You interrupt me. Does anybody know how to turn Siri off? I said our series of classes tomorrow, and Siri thinks that we're talking to her. Quite annoying. Okay, but this technology is the same technology of what I've showed you in those videos. It's just a lot simpler. Okay, it's a lot simpler technology, or it's a lot simpler mechanism. I don't know if I'd say simpler, because these things are getting pretty complicated. The technology that makes these non-axis sensors is very similar in the same family, in the same genre of that stuff that I showed you. All right, so let's see here. Let's see, maybe I can look at your questions, and then after looking at your questions, this is probably going to go a little longer than normal, but this is a cool topic, and I don't know if you guys are behaving yourself over there in the chat room or if you're not, But let me come back over here and look at some of your questions. And then after I look at your question, I'll try to answer your questions, and I'll go and I'll show you more specifically how we built those motors. Like you say, how could you build a motor like that? Nobody put anything together. They were batch fabricated a bazillion at a time. You got the wafer out, you put a signal on them, and they ran, okay? Okay, so let's go back and see what your questions are. I don't know, is anybody even out there today? Okay, we got some people that are watching. All right. Let's see some questions here. Hello, hello. Oh, large cup of iced coffee. Okay, how do I make this? I make like, this is completely, this tumbler is filled completely up with ice, as much ice as you can get, and then 8 shots of espresso. Okay, so I fill it up with ice, and then I fill it up with coffee, and then I don't drink it immediately. I make this first thing in the morning. Then as I'm enjoying my morning cappuccino, this is sitting there just kind of letting the ice melt down a little bit, and then I bring it to work, and then I start drinking it. So you got to let it dilute a little bit. You got to let a little of that ice dissolve to get the right amount. Okay. Hello from the Dominican Republic. Hello. Hello from India. Hello, Jason. Hello, Cameroon. Wow, Bangladesh, Michigan. All right. Is this live? This is live. Did you not see? Did you not see? Live over here on the screen. Look, live, Shop Top. We are live. Actually, there's like a 15 or 20 second delay. So this is live as we can get. Hello from Egypt, Ireland, Belgium, India. We got a worldwide audience here. Okay. Dalengrand, Canada. Okay. It is unclear. What is unclear? Hello. Your amazing teacher. Thank you. Yes, still working. Don't spill your coffee on your Mac. I know. I hate it. As much as I hated, this was a really expensive microphone, and as much as I hated knocking it onto the floor, I don't hate it as bad as when I spill my coffee, because this is like precious. This has got to last me all day. Okay, boom. Can we transmit Raspberry Pi camera footage? You cannot send pictures over the Iridium satellite network. The Iridium, you can send 20 byte packets, maybe 1 or 2 a minute. You send data telemetry, you do not send pictures. Okay. Hi, a lot of hi. Sorry if I'm missing your question. How are the small parts made from sand particle? Okay, guys, I'll show you in a minute how we make them. All right, I'll show you in a minute how we make them. Good question. Info overload. What? Info overload? No. Should I have broken this down into like 20 lessons and kind of broken it to you gently that there's this level of complexity going on in the micro world? I think most people don't know that this type of stuff is going on. Okay. Go away. All right. Hey, what's up? Finally caught you live. Yeah. Are these videos from a microscope? They are from, the ones where they are live are from an optical microscope, like a really powerful optical microscope. It was probably like $150,000 microscope. To get the really good pictures, you use a scanning electron microscope. But the problem is with a scanning electron microscope, you can't operate them while they're having their picture taken. Because to get their picture taken, you got to coat them with gold. And once you coat them with gold, then they don't work anymore. So we would do that to take their picture, but we couldn't get the scanning electron microscope. But the things you saw today were live, they were real, they were not simulations, and they were from very expensive microscopes. And so it's kind of funny. What color are Micromachines? Well, they're pink on a green background. And that's just what color they are. But because they're pink on a green background, people think that they are a simulation. Hey, just joined. Todd just joined in. Will you be producing? Yes. Who was that? Todd, where have you been? We debut the lessons tomorrow. Tomorrow we release those. Go down in the link, get your B&O 055, and then you'll be a couple of days late, but you can join how to do that, okay? East Tennessee, all right, Glenn. I love the way people in Tennessee talk. It's a very sweet language that is spoken in Tennessee. Okay, nice talking. Hello from Portugal. Hello from Nicaragua. I wish I could say that better. Okay, you guys, I'm not seeing a lot of questions about nanotechnology. I'm seeing a lot of hellos, but you guys ask some questions because I'm fixing to go into the kind of second part of this about how we build these things. But you need to kind of give me some questions here. I'll give you a second because I know there's sometimes I get, why don't you ask me? Come on, and then there's a 30-second delay. So when I say ask me questions, I got to give you 30 seconds to ask a question. Okay, I'll tell you a little bit where are these things used. You know, almost all cars have skid suppression. So if your tires are saying you should be going straight, you can detect that you're starting to slide, and then you detect that using this nanotechnology. And in fact, that's like these non-axis sensors, and then the system taps a brake to get you going back straight again. And so they're used there. They're used to fire the airbag. These projectors where you get the big projectors on screen from a computer, those have millions of those little mirrors. Like, remember that little mirror I showed you? Imagine having an array of millions of those, and those mirrors are fluttering, and that's what creates the images that you see on those really nice modern projectors. They're used like in your cell phone. Right, you know how your cell phone, like my cell phone kind of came on because it knew that it had been picked up. There's accelerometers in there. And literally, like I said in my older, fatter version, that was probably 20 years ago, and I said in 5 to 10 years they're going to be part of almost every product you buy. They are in an incredible number of products, but you don't know that they're there because you don't see them. Okay, and because you don't see them, you don't know they're there. But they really are in a whole lot of different things. Okay, let's see. Okay, asking about how we make these things. I'll talk about that in a minute. Okay, how are the small parts made? I'll talk about that in a minute. Good question. Okay, yes, these are from a microscope. Okay, a bunch of hellos. Yes, in Tennessee you speak slowly and gently and kindly. It's a very attractive cadence to listen to. I don't like these yappers, these yappers, like especially on TV. Can't handle that. I can't handle that. One of the reasons I don't have a TV in the house. Anything to say about graphene in real world applications? I'm really excited about graphene. I am so excited about graphene. I have a little bottle of it. This was insanely expensive. I think this was like $400 for this little bottle of graphene. And I have gotten tangled up here. What I was interested in doing is kind of like some supercapacitor applications. So when I find time, I'm going to try to make supercapacitors. So yeah, I have graphene, and I think that one day it'll be great. Not really sure where it's being used. How do you build it? I'll show you that. What kind of home automation could be built with nanotech? Well, basically, a lot of your sensors already have nanotech in them, like thermal imaging, thermal sensors, accelerometers, gyroscope, magnetometers. A lot of these sensors, like your little eLego kit, a lot of the stuff in there already has this nanotechnology in it. Yes, sensors and actuators are made of those. Yes. Can you have you seen the motors that hook up to moth wings to remote control the insects' flights? I probably haven't seen that. Oh, okay. All right. I'm going to show you one more from the vault. Okay. This is like, of all the things I've done in my life, like I've done a lot of crazy things, and I've been on like TV, and I've been like all over the world, and like I was kind of like Mr. Celebrity. But the thing that I did that got more attention than anything else that I ever did, let's see if I can call it up. All right, I'll show you this one. Give me a second, please. Again, I am trying to produce this as I am speaking. And now we need to come over to a full screen. Let's see if this is, I think this will work. And I will get out of your way. Now what I'm going to show you guys, this is real. This is not fake. This is real. And again, it's hard to make people believe that it is real. So I had so much trouble making people believe that these machines were real that I decided, okay, I'm going to go get something really, really small. Like, what is something really, really small? A dust mite, right? You've got dust mites all over you. Like, these aren't like cooties, but you do have dust mites. Maybe I should. Maybe I'm telling you too much stuff today. But you are covered with dust mites, and it's a natural thing to have on you, and they're everywhere. And the reason you don't see them is because they're so small. But you can get those, you can collect those dust mites. And what I did was I put the dust mites down on the Micromachines. And the amazing thing is they would run around, and sometimes we'd see them pick something up, like we'd see them run over, pick a gear up, and like run off with the gear. But what I did was I put a dust mite on these Micromachines. And look at him. You see he runs by over there? Look at him go. He's a fast little guy. Now the first time he just ran by. Did you see the first time he ran by and he was carrying one of these little parts of the motor he was carrying, and then as he ran over this thing he dropped it, okay? But my goal was to make the world's smallest merry-go-round and then give a dust mite a ride. That was my goal, okay? So the first time he runs by it, the second time he runs over it and doesn't stop, and the third time he runs up, he stops, and I give him a ride around. Boom! Do you see that? World's smallest merry-go-round. Let me tell you something. Making the world's smallest merry-go-round was the easy part. Getting a dust mite to crawl up on it and go for a ride, that was the hard part. Now, we didn't want to scare him, so we went kind of slow with it. And so if you look, we kind of give him a nice easy ride, you know, just like a simple one. Do you see how we just kind of go around there? We just go around nice and easy. And then we go backwards, so we went both directions. You see that? We went forwards and backwards. And then we stop, and then he goes off. No dust mites were harmed in the filming of this nanotechnology video, okay? But then that we got that under our belt, we thought, well, I wonder if you can make a dust mite dizzy, okay? So then he comes back, and this time we spin him up to a couple of thousand RPM and shake him around like, really? Oh my goodness, look at that. And stop and shake him around. And you know what? Look at him. He got disoriented. Like, where am I, man? It took him like 5 or 10 minutes to get his orientation back. And so, yes. Ooh, and this is the aphid, okay? And do you see how the aphid is over there bending these things and walking all over? The aphid is a rather ugly creature. Okay, so the aphid is a rather ugly creature. All right, so let's come back here. And let's get back to our business and see if I have any other questions. I'm going to show you guys in a minute how we are going to, how we run these things, okay? Or how we make these things. So you were talking about the moth flying the moth. Yeah, some of those things are kind of like what I just showed you, sort of cheap publicity stunts. The dust mite thing, it was a cheap publicity stunt, but it really worked. If sensors are made of these, then how many of these are in there? Well, like for the 9-axis sensor, the BNO055, it has 9, but each one of them could have a very large number of mechanical elements. So one sensor might have 1,000 of mechanical elements or mechanical features. What influence with electromagnetic fields on substrates in nanotechnology? They're made out of silicon, which is not a magnetic material, so they're not really susceptible to magnetic effects, but they're very susceptible to electrostatics, because that's how we operate them. Like, you think a motor in the real world works with magnetics, but we can't scale magnetics down, so these things work with electrostatics. Okay, so you apply voltage, that voltage creates a field, that field creates a force, that force creates a motion. Okay, that's what, hey, you guys share this with people. I think this is pretty good, cool stuff. So share this video. If you're going to share one, share it. I think this is pretty cool. PETA would get you for that these days, and I would tell them to kiss my big hairy hand. Okay, yeah, kiss my hand, kiss my ring if you don't like it, because I don't care what PETA thinks. Now, what I am is I'm very good to my animals. I've got chickens, and I care deeply, and I'm a very good steward of my animals, but I don't care what PETA thinks. Okay, so let's see here. All right, so let's get in, you guys. Let's get in and learn how we make these things. So maybe, what's the best thing to do here? Can you see this? How do I do this? All right. I hope this is the right way. Let's see. I am afraid this is going to be upside down. Guys, would you be patient with me and let me see if I could spin this thing upside down, because I fear that you are going to be looking at this upside down as I talk. I should have thought about this. If this was a real professional operation, this would have been done earlier. Okay, let's see if I can rotate. That's flipping it. I'm sorry that I didn't. Here we go. So I'm trying to make it upside down. Okay. Now let's see. Like if I draw something. Okay. There. All right. So how do we build these things? We build these things on silicon wafers. And first of all, how do you build them a bazillion at a time? Well, it's done optically. Okay. So imagine that I draw something. Like imagine that I'm going to draw a transistor. So a transistor has 3 terminals. This is a gate, this is a drain, and then this is a source. Okay, and you don't have to really understand this, but just kind of take my word for it that I'm kind of showing you how that you could make a transistor. And so kind of go with me on this. All right, so you see I've got, now I can come and I can bring a wire in, like tiny microscopic wires, and I could connect to these 3 things and I would have a transistor. And you could design this very, very carefully. And then of course you don't come in and connect to the transistor directly, that on the circuit you interconnect with on the chip interconnection, and that's how you hook up a billion at a time. But here I just made 1. Well, once I make this and I'm drawing it on a CAD screen, right, nice and big, but then it goes on to a negative. Like remember in photography how you had a negative, and you might have a negative this big, and then you would take it to the darkroom and then you would enlarge it, and then you'd make a big 16 by 20 picture by taking your negative and running through optics to enlarge it. But what we do in the microelectronic world, we take that negative, it's a negative, okay, it's an object that you could hold in your hand. Like this is a silicon wafer, but the negative would be kind of like this big. And what you do is, instead of enlarging it, you make it small. So I take this thing that I've designed, I put it on a negative, and then I use optics to take it down to teensy dimensions, like, you know, almost down to the atomic scale, you know, very, very much smaller than a micron, you know, like 1/10 of a micron, sub-10th of a micron type dimensions. Well, how do I do that? With light. Okay, optically. I shine through something that is in the real world, and then optically I can project this down. So I can take this thing that I drew and I can project it down onto the surface of the wafer, okay, using optics to a tiny, tiny, tiny degree. Okay, now, so the first part of it, how do you get small? You get small optically. Okay. Now the second thing is, how do you build a billion at a time? Well, I'm a designer and I kind of design the transistor. Okay. And I go in and I do all the physics and I do all the atomic level stuff, and I create this transistor, this little switch that works perfectly. And then I give it to the next guy over, and he doesn't care about it. He just treats it as a little black box. And then he starts copying and pasting it. He doesn't care how the transistor works. He just copies and pastes it, and then he hooks it up. So maybe he makes something that would be a flip-flop, where he takes 4 of these little black boxes, he copies and pastes, and then he connects them in a certain way, like with 2 inputs and 2 outputs, and then he creates a little black box based on my black box, and this little black box is like a 1-bit memory cell. Okay, now this then goes to the next designer, and what he does is he doesn't even know there's such a thing as transistors. I'm exaggerating, of course, but he doesn't even know there's such a thing as a transistor. And what he does is he copies and pastes these boxes that this guy made, and it's similar. So design is happening at all these different levels, to where the guy that's up at the top, he just grabs this thing and grabs this thing and grabs this thing. So it's a bunch of cutting and pasting, so that you don't design a billion different transistors. You design one transistor, and from that one transistor you make 5 functions. And then the next guy, he takes those 5 functions and he makes bigger boxes. And then the guy above him takes those and makes bigger boxes. And so in the end, the guy at the very top designing the chip, he might just be sitting there having a latte. I think I'll get a cereal bus, and I think I'll get some of this, and I think I'll get this microprocessor. And he's just putting these blocks together. So it's about hierarchical levels, like if you think of folders inside of folders inside of folders, hierarchical levels. So that's how you get complex. You have billions of transistors, but it's cutting and pasting, and you build them all at the same time. Okay, so cutting and pasting, you get many, and then optically you get small. So that's how an integrated circuit is made, kind of looking down on it from a design perspective, looking at the surface. But then how are they built? If you think of a cross section, how do you build them coming up as a cross section? Well, let me show you that. Okay, let me show you how you build them. And I've shown you that if you can build one transistor, you can build a microprocessor. So let's talk about how we are going to build a transistor. I sure hope you guys were seeing that. That was some great stuff. I hope it was showing up. Okay, so I'm showing you from the side. So what is this crazy lack of focus? What is this insanely poor focus that we're getting? Okay, so I am showing you a cross section of the silicon wafer. You are looking at a blank silicon wafer from the side, and so this is silicon. Okay, this is silicon. That was a horrible silicon. This is silicon, and it is a semiconductor, which means it can be a conductor or an insulator. Well, I'm not going to put any impurities in it, and so at this point, it is an insulator. Okay, it could be a conductor, but I make it to be an insulator. Now, silicon, if I expose it to high temperature and oxygen, it turns to it turns to glass. Oxygen and temperature. But what it does is, at the surface, it begins to oxidize the silicon wafer, and so you grow this perfectly controlled piece of glass on the wafer. Oxygen and temperature. Silicon becomes silicon dioxide. Silicon dioxide is glass. All right? So now, I take that picture of the transistor and I project it down on the wafer. Now I put some photosensitive material on here. Okay, I guess I should do that. So I put some photosensitive material on here, just kind of dump it on there. Then I project my image, and in certain places where the light hits, I can open it up. I can develop it like a dark room. Okay, I can open it up and I can expose that oxide. to the outside world. So this area is protected by the photoresist, okay, and this area is open. Now I dump this in an acid. What does an acid do? An acid dissolves glass. And so where this is open, this is going to happen. And so now I have this. And then I'm going to take the photoresist off. Okay. So now what did I end up with? I have a piece of silicon, and then I have glass on top of it that is an insulator, and then I have holes down to the silicon. Now I'm going to skip steps. You get the idea that you deposit layers, you photo pattern them, and you etch them. So what I'm going to do now is I'm going to do that with metal. I'm going to put metal down, I'm going to photo pattern it, and I'm going to etch it. And so here I have a metal connector here. Here I have a metal connector here, and then I have a metal connector here. Okay, and these are the 3 terminals of the transistor. Now this is a metal, so it is what? Conductive. This is a metal, so it is what? It is conductive. It is conductive here. But if I put a voltage between here and here, like put 5 volts here and ground, does current flow? No. Why? Because the silicon, I made an insulator. All right. But what if I come up here and I put plus 5 volts here? This is going to bias this positive. Positive attracts what? It attracts negative. So if I put 5 volts here, all of a sudden that attracts all of these electrons up here, okay, right to here. But this insulator, they don't ever get to the 5 volts. They're trying to get to the 5 volts, but they can only get to the insulator, and then they stop. Okay, because they can't go through the insulator. But now that I put all these electrons here, what do? They create a conducting channel. This is the magic of how an integrated circuit works. So now if I put plus 5 here, you've got current flow, you've got current flow, you've got current flow, as long as I've got the 5 volts here. But when I take that 5 volts off, and if I ground this, then those electrons go away because they've got no reason to be there, and now this is an open switch. Okay, so I just made an open and closed switch. Now if I can make one, now I can make 1 bit, and if I can make 1 bit, then I can make this block, and so then you just start designing. But that's how the transistor is made. All right, so what does this nonsense have to do with nanotechnology? So this is kind of what we were thinking. So I'm going to have my silicon. Oh, this camera is going to be the death of me. Okay, so here's my silicon, and I'm going to expose the silicon to heat and oxygen, and what am I going to get? I'm going to get a glass layer here. All right, I'm going to get a glass layer here. Now, what can I do? You remember how I can photo pattern something? So I'm skipping steps, but I'm going to photo pattern this. Now I'm going to come and I'm going to put polycrystalline silicon. It's like just an amorphous form of silicon. I'm going to put it down and I'm going to pattern it. All right. So I'm going to put it down. It goes down everywhere. And then I'm going to photo pattern it. Well, it's even going to go down in this gap. So you see now it's going to go all the way down like that. Okay, so this part of the silicon is anchored to the silicon substrate. This part is anchored to the silicon substrate, and this is sitting on top of the glass. Here's the brilliance. Here's where the magic happens. Silicon is immune to acid, like hydrofluoric acid doesn't touch silicon. Hydrofluoric acid dissolves glass. So if I take this and I dip it in hydrofluoric acid, what happens? It dissolves the glass. And now what am I left with? I'm left with this mechanical, like diving board. Okay, kind of boring compared to the things I was showing you earlier, but this is the fundamental starting point that allows you to build the motors. So this is a diving board. Well, what interesting thing could you do with a diving board? Well, imagine that you made an electrical connection here, and then also what I'd done that I didn't show you, I put a little electrical pad here. So I have a connection here, and I have a connection here, and this is free to move. Well, what if I go like this? If I go like that, this is going to, that gap is going to change, right? Because if I move it up, the diving board is going to tilt down. And if I measure the capacitance, what is the capacitance? The capacitance is equal to epsilon, which is just a constant, the area, which is the area of this thing, over D. And what is D? D is the gap. If I measure capacitance, I can calculate D. And as this thing moves, D is going to change. And so what I've just done is I've made an accelerometer. Okay, an accelerometer, like back to our 9-axis sensor. This is kind of like the fundamental concept behind an accelerometer. Now we get really, really fancy and we get 3-axis, and you know, we can spend our lives making better and better accelerometers, but this is showing you kind of the core thing down at the sort of like getting towards the atomic level, how things work. Okay, so how could I make that gear? Let's see. We start with a silicon wafer. Okay. And now what I'm going to do is I am going to put my glass down. Okay, I'm going to put my glass down. And then what am I going to do this time? I'm not going to bore down to the silicon. I am just going to put my polysilicon down. And then I'm going to pattern that polysilicon to look like a gear. So you're looking at the cross section of the gear now. Now after that, I'm going to etch this like this. Okay, now if I just got rid of all the glass, the gear is going to float away. So I'm not going to get rid of all the glass. I'm just going to do a quick dip in the acid, and it's going to kind of come in and etch back like this, and then etch back like this, and then maybe out here it would kind of etch in a little bit, and maybe over here it would etch in a little bit. But what's the good news? The gear did not float away. Okay, the gear did not float away. Now, if I came in and put polysilicon down now, it would fill everything in, and then I would have a gear affixed to the substrate, but it's never going to spin because it doesn't have a hub. So what I'm going to do is I'm going to come in and I'm going to grow a little bit of silicon dioxide, just a tiny amount of silicon dioxide. Okay, and so now I have a tiny bit of silicon dioxide, like that. All right, and now I'm going to put polycrystalline silicon down, and so I'm going to put the polycrystalline silicon down, and it fills in, it runs in, it doesn't go line of sight, it will fill in. So it fills in not only up here and not only down here, it fills in that undercut region there. Okay, so now this is silicon, polycrystalline silicon. So what did I just make here? I made a hub. Now at this point this gear can't spin because it's polysilicon mechanically connected to oxide, mechanically connected to polysilicon. No spin. What can I do? Hydrofluoric acid. And then that hydrofluoric acid will come in, and this time we leave it a long time, and it etches this silicon dioxide away. And I kind of, okay. And so what am I left with? I am left with the gear, okay. I am left with the gear, and it is constrained with a hub, but it's free to spin. And so then that's kind of just a quick picture of how we made something that could spin around like the gear. But it's just like you just do more and more complicated and more steps and more things, and then you just get more and more things. But the thing to see is you're doing it all at once. So when I make one gear, I make a bazillion. If I hook the gear to a motor, it's all done at the same time. So when this thing comes out, you didn't have to go and put this gear on here under a microscope. These things come out ready to run. So just like all those videos I showed you, those things were all made, batch fabricated. They came out of the fab and they were ready to run. Okay, let's come back up. Let's see if you guys have any questions. Man, I hope there's interest in this. Okay. What are your questions, man? Is there anybody even out there? Can you use oil? Yeah. Can you use oil to lubricate these things? You really can't, because the oil is too viscous. The oil is too viscous, which means it would just kind of glue it down. So what you would do is, these things are so small, how do you lubricate at a, start nano dimension? Well, what you do is, there are things that are called self-assembled monolayers, and what they are is like a little, and you can't see what I'm drawing, I'm sorry. So what you do is you do self-assembled monolayers. So imagine this was the gear and this was the area of region that's going to be rubbing. Well, what you can do is, even like this is kind of like almost like Teflon would be an example of something that's, I'm not saying Teflon is a self-assembled monolayer, but it's getting kind of like to some pretty fancy science. But what you do is you can make these little strings of atoms, like almost like an individual string of atom with a bigger one here, and then an atom, and you can kind of build these things where you create kind of this little floating sea of atoms on these strings, self-assembled monolayers. And what they become is, they become like a lubrication. They act like a lubrication, so you're not just grinding rough surfaces against each other. So we had great success using self-assembled monolayers. We actually went in and did some stuff like trying to put Teflon so you get real smooth things. We went in, you can go self-assembled monolayers, you can go smooth, or you can go hard, right? And with hard, we would like put diamond coatings in there. We would do like chemically vapor deposited diamond to create a very hard surface. So we worked a lot on increasing the longevity of those machines like I showed you, but in the end we decided, man, it's a lot easier to do design work than it is to do material science. So we said, let's just have a rule that we're going to design things with no moving parts, no rubbing surfaces, no matter how hard it is. Just imagine we're going to build anything imaginable, but we're not going to have rubbing surfaces. And so that was what we did, as opposed to trying to solve rather than try to solve the lubrication problem. Okay, now we're getting some good questions in. Thank you. Okay. All right, so let's answer this question. What is the difference? Okay, how do you make a motor? Okay, so just say that we can have things on the substrate and we can have things floating. So I'm going to draw something. Imagine that this is connected to the substrate. Okay, this is connected to the substrate and this is connected to the substrate. I wish I could draw better. And then imagine this is floating. Okay, this is floating. Now by floating, I mean it's not touching the substrate. These two are touching the substrate. This center one isn't. Man, I desperately wish that I could draw better. I wish I was one of these guys that could draw better. And this is sort of suspended by flimsy springs. Okay, so this is suspended by very flimsy springs. Okay. So the end of the springs are connected to the substrate. The end of these springs are connected to the substrate, but this is floating above the substrate. This, and this. All this is above the substrate, but these are anchored to the substrate. What happens if I put a voltage between here and here? A positive and a negative what? They